Okay, last time with probability rules, we looked at the addition rules, and today we're going to look at the multiplication rules. So if you remember our previous lecture, we looked at ME, which stood for mutually exclusive, and we needed to know if it was mutually exclusive or not to correctly apply the addition rules. Today, what we want to look at is independent versus dependent, okay? So let's talk a little bit about what we mean by independent events. Okay, the definition. Two events A and B are independent if the fact that A occurs does not affect the probability of B occurring. Does not affect the chance or probability of B occurring. Okay? This is independence. So two events A and B are independent if the fact that A occurs does not affect the probability of B occurring. Okay, let's do a couple of examples. And then all I want to do is look at this example and decide, are these independent or not? Okay? So the first example is draw a card, get an ace, replace it, draw a second card, and get an ace. Okay, so draw a card, draw an ace, replace it, and then draw an ace again. Okay, so if you look at this example, we're going to draw a card and get an ace. Then we're going to replace that card in the deck, and then we're going to draw and get another ace. All right? Now, is the probability of drawing the second ace affected or altered by the probability of drawing an ace the first time?
Did we put the first ace back?
Replaced it. Yeah.
Oh, so yeah, no.
So no. Does everybody see that? I have a 4 out of 52 chance of drawing an ace. If I replace the cards and I draw again, I still have the same probability, right? So these events are independent. Okay. The fact that the first one occurs does not affect the chance or the probability the second one does. All right, example 2. Flip a coin and get a heads. Flip again and get a tail. Okay, flip a coin, get a heads. Flip again, get a tails. The fact that we got a heads the first time, does that alter or change the probability of getting a tails the second time? What's the probability of getting a tails? It's always 50%, right? That's not going to change, no matter what happened here, right? So again, perfect example of those events are independent. Okay, example 3. Draw a card and get a diamond. Not replace it. And then draw another diamond. And the question is, are these independent?
No,
Why not?
because it changes.
The probability goes down if you don't replace it.
There's two reasons why this one's not, right? So if I do get a diamond that first time, how many diamonds are left on my second?
3.
There's only 3 left. But also, if I don't replace that card, I went from a denominator of 52 cards here, and now I have a denominator of what? 51. Does everybody see that? So the probability has changed.
Well, there'd be 12, not 3. You said 8 diamonds, there's 13 diamonds.
Oh, okay, I'm sorry. So 13 out of 52, but then here 12 out of 51, right? So the numerator and the denominator have both changed. So these are not independent, they are dependent. Okay? And example 4. Get a 100 on your first stats test coming up. Get an A in the class. Are these events independent or dependent? Is the fact that you get 100 on your stats test going to affect the chance of you getting an A in the class? Yeah, it's going to definitely affect it, right? How do you get your average for your grade? You average your test. Well, here's your test grade. So whatever you get on your test is going to affect the probability of you getting an A in the class. Okay, so these are definitely dependent. Everybody see that? Question?
But the probability of you getting 100 on the stats test doesn't affect your probability of getting an
The fact that this occurs. So the fact that A occurs. So we're assuming that you did get 100. Does that affect the probability of you getting an A? Yes. Okay. Let's. Do we have any gamblers here? Let's take a look at a gambling question. How about, okay, how about this example? When you play roulette, for instance. Okay? So people are betting, and let's say, I don't know, red comes up like 10 times in a row. Red, 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 right? And they have a little display, right? And then all of a sudden, everybody around's like, oh, okay, let's bet on black, right? Everybody understand that example? So red has come up a bunch of times in a row, and then people around the table are like, okay, let's bet on black, right? Why are they doing that? Is the probability that black comes up on this flip any different from the previous flips? No, okay? It's still the exact same probability. It doesn't change. So these are independent, okay? Red could come up 1,000,000 times in a row. The chance that it comes up on the 1,000,001st time is still 50-50, or whatever it is, depending on how many green spots it had. Okay? So that's independent. Any questions on that? Okay, so here's our multiplication rule number 1. When two events are independent, here's our rule for probability. The probability of both occurring we'll write that probability of A and B is equal to the probability that A happens times the probability that B happens. Multiplication rule number 1. When two events are independent, the probability of both occurring, probability of A and B, is equal to the probability of A times the probability of B. That is our rule for independent events. Okay? So, example number 1. Drawing a card and getting a diamond, replacing it, drawing a card and getting a 7. Okay? So example 1, let's calculate the probability. So we're going to draw a single card and get a diamond. We're going to replace it and draw a 7. And I want to know what's the probability of these two things happening. So according to this rule, it's the probability of getting a diamond, right? What is the probability of getting a diamond? How many diamonds are there? 13 out of 52. Times the probability of getting a 7. What's the probability of getting a 7? 4 out of 52. Okay? And you want to reduce that and multiply that together. This is kind of nice because 13 goes into 52 4 times.
Yeah.
Then the 4's reduce out, and you just get 1 out of 52. Okay, multiplication rule, independent events. Next example. Flip a coin, get a heads. Flip a coin again and get a tails. Flip a coin, get a heads. Flip a coin again and get a tails. Calculate that probability for me.
One-fourth,
1/4. How did you get that?
1/2 times 1/2.
The probability of getting a head times the probability of getting a tail. The probability of getting a head is 1 out of 2 times the probability of getting a tail is 1 out of 2. So your answer is 1 out of 2 times 1 out of 2, which is 1 out of 4. Okay? Now let's say I come to you and I say, you know what, I don't believe this rule. I don't think it's right. Is there another way that you could show me that the probability of getting a head and then flipping again and getting a tail is equal to 1/4? What's another way you could show me that?
Sample space.
Sample space. Awesome. What would the sample space look like for this? I'll get you started. Head, head. What else?
Tail.
Head, tail, right? Tail, tail, and what else?
Tail.
Tail. Is that every possibility? There's 4 things that can happen, right? How many times does this happen? You get a heads first and then you get a tails. Just 1 out of the 4. Okay, so this multiplication rule is just showing what we already knew how to do with the sample space for this problem. Okay, out of the 4 possibilities, this happens once. Okay, that is our multiplication rule for independent events. Great, let's take a look at dependent events. So, when we don't have independent and we have dependent, the rule switches a little bit. Okay, so for dependent events, it looks like this. The probability of A and B occurring is equal to the probability of A times the probability of B. So far, how close are these formulas? They're identical so far, right? So where the change occurs is right here. You put a vertical line, and that vertical line stands for given that, and I'll talk about that in just a second, and then A, okay? This piece here is what we call conditional probability. The probability B occurs given that A has occurred, okay? So this little guy here stands for the probability B occurs given that A has occurred. Okay? It's the conditional probability B occurs given that A has occurred. So you assume A did happen. All right. Let's do an example. Draw a card and get a heart. Don't replace it and draw and get another heart. Okay? So let's get a heart. Don't replace it and get another heart. All right? So a lot of these problems will have to tell you with replacement or without replacement. So we're saying without replacement. Okay, with the standard 52 cards, how many of them are hearts?
13.
13. Okay. So I have the probability of drawing a heart. Then I come to this guy. What is the probability of drawing a heart given that the first card was a heart? I have now 12 hearts left, and how many cards do I have left? 51. Okay? That's how that works, conditional probability. So the probability of the first card being a heart is 13 out of 52, times the probability the second card is a heart, given the first card was a heart and you're not replacing it. There's only 12 hearts left, and there's only 51 cards left. Okay? And then let's reduce that down. It comes out to 117. On your calculators, there's a second math frac key, and that will reduce fractions for you if you ever need to use that. Okay? Next example. Probability of getting an ace and getting a 7 on the second card without replacement. So probability of an ace and then a 7 without replacement. Okay? So again, without replacement, that puts us into definitely dependent. The probability of getting an ace is there's 4 aces out of the 52 cards, times, given that the first card definitely was an ace, how many 7s do I have left? 4. And how many cards do I have left? 51. Okay. And that's it. And then reduce this down. You get 4 over 663. Okay, great. Next question. Let's do 3 aces in a row without replacement. Three aces in a row without replacement. Okay, again, you're just using this conditional probability formula and it keeps going. So what's the probability the first card is an ace? 4 out of 52. Times, what's the probability the second card is an ace given that the first card definitely was an ace?
3 out of 51.
3 out of 51. Times, what's the probability the third card is an ace given that the second card definitely was an ace? 2 out of 50. Does everybody see that? And it just keeps going. Okay? And what does this come out to? 1 over 5525. Okay? Any questions on that one?
Yeah, so if we get this on a test, would you want us to leave it in the fractional form? Or?
Yes.
Okay.
Yeah. Just reduce it down. Okay. The last example I want to look at is very similar, and sometimes students get confused.
Just want to get my voice on the tape.
Okay, so let's take a look at these two examples. How I do this example, let's say it's given that 10% of the population is left-handed. Okay. What's the probability that 3 randomly selected people will all be left-handed? Okay, how would you guys do this problem? 10% of the population is left-handed. What's the probability that 3 randomly selected people in the whole world, we're just going to pick 3 people, what's the probability that all of them are left-handed? How would you do that?
Is there
replace the people that you randomly selected?
Okay, so that's the question. This sample is so huge, right, that the percentage isn't going to change, okay? And I'm going to compare this problem to a smaller sample problem in just a second. But when the population is so big and we have a number like this, you just use your multiplication rule, okay? So the probability that the first person is left-handed is 0.10, times the probability the second person is left-handed is 0.10, times the probability the third person is left-handed is 0.10, okay? It's just multiplication rule. You treat it as independent, okay? And what does 0.10 times 0.10 times 0.10 come out to? 0, 0,
0,
0, 1. Okay?
Is it okay to leave that as a fraction?
Yeah, you can leave that as a fraction too, like I've done all the other examples. 1/10 times 1/10 times 1. Right. 1, 2, 3. Okay. Now, compare that to in a class of, let's say, 30 students. 3 are left-handed. Okay? In a class of 30 students, 3 are left-handed. What's the probability that 3 randomly selected students will all be left-handed? Okay, now how does this problem change compared to the last problem? This problem we have exactly 30 students and we know that 3 are left-handed, okay? What's the probability the first student we pick is left-handed?
3 out of
3 out of 30 times, given that that first student was left-handed, what's the probability the second student is left-handed?
2 out of 29.
2 out of 29 times
1 out of 28.
1 out of 28, right? And check that answer. And multiply that out and see what you get. What'd you get for a decimal? What'd you get for a decimal?
0, 0, 2.
0.0002. Okay, so comparing those. Very, very, very close, right? We're still talking really close, but different. So when you have the actual sample and you know the denominator and its dependent events, this is how you do it, okay? If you have this huge population and they just give you a percentage, then just treat it like independence, okay? Does that make sense? All right, any questions on today's material? Multiplication rule, so we should be multiplying, yes?
I was just wondering, how did you get from 3 to 2 to 1 in the...
In this problem?
Yeah.
Yeah, okay, so the probability that the first student is left-handed is 3 out of 30. And if we assume that to be true, take that person out. The probability that the second person is left-handed, given that the first one was left-handed, there's 2 students that are still left-handed out of only 29 left.
Oh, yeah, okay.
And then you assume both of those are true, and then there's only 1 left.
Alright.
Other questions? All right.